Hello everyone, I'm Max, and recently I've made a TEDx video, TEDx talk about the fly-by-wire system on the A320 and how it can improve aviation safety. And today I am going further with the PowerPoint I've made for TEDx and talk just in a bit more detail about the entire system that is being used on A320 and overall all types of fly-by-wires. So firstly, over the basics, aviation is inherently a bit more dangerous than ground transport, a bit more risky than ground transport, and that's mainly due to two reasons. First, it's just the speed. With cars, then maybe you can go up to 120 kilometers per hour, but with most airliners, you can go up to 950, and for the Concorde, of course, 2500. And this just means significantly more kinetic energy, and if you crash, which is essentially losing all that kinetic energy, is going to be significantly more catastrophic. Crashing at 120 kilometers per hour is very different from crashing at 950 kilometers per hour. And although this is a very, very big generalization, but the idea is the same. At higher speeds, it's a bit more dangerous. And a more important part is the complexity of airliners and aircraft. For example, for a car, there's around 30,000 parts, but for 747, there's 6 million and even more. So, even though aviation components are significantly more tested and more redundant compared to potentially car parts and components, there's simply more of them, and that means the potential of failure is significantly higher. That's why there are ETOPS requirements, and also why ETOPS was not implemented in the first place, and also MEL, minimum equipment list, in aviation. Conventionally, this is the conventional way for pilots to provide control for the aircraft. The pilots will provide input, and that will be pitch, yaw, and roll with the stick and rudder, and also thrust, trim, and utility parts such as landing gear and flaps in other forms of levers or switches. And those things will lead cables, and the cables will physically move. For example, if you go to the 737 landing gear bay, you can see all different types of cables that will move around when the pilots provide input. For example, for the ailerons, and for older 737s, the spoilers and gear and all different types of hydraulic actuators and more. And this will lead to actuators. For most airliners, there are two ways of providing controls with actuators. The first is just to rely fully on hydraulics. That can be, most newer aircrafts will rely fully on hydraulics, except the 737, which does have manual reversal, which I will talk later about. And with full hydraulic reliance, there's usually 3 sets of hydraulics, and the cables will control the hydraulic actuators, for example, for nose wheel steering, and that will lead to the response from flight control surfaces. Another way of providing control for larger aircraft and faster aircraft is by mixing hydraulics and manual reversal control tabs. And one example of that will be the DC-9, which does have hydraulic systems, but at other times, the pilots will also use the control tabs with manual reversal. Manual reversal is to implement tabs, the control tabs, on flight control surfaces that actually goes against the opposite way of your intended direction of the flight control surfaces. For example, you want to pitch up, so the elevators at your tail want to go up, but the control tabs will in fact will point downwards. Why is that? Because the control tabs are intended to move and drive the flight control surface to its intended position. For example, because the control tabs are pulling a higher AOA, angle of attack, than the flight control surface themselves, it will actually move the flight control surface up for a pitch up movement, even though it's pointing down. It's very convoluted, but if you can look at how the control tabs work on the 737 and also the DC-9, and it will be very clear. And as a result, that will have a response on the elevator, rudder, and aileron, which are the primary 3 control surfaces for an aircraft, and also trim and landing gear actuation, potentially. And as a result, there will be a physical response of the aircraft. There is, your elevators goes up at the back, then your nose will point up, and the opposite will happen, and your nose will point down. And this is an example of how the entire system works on the 737 MAX. The 737 MAX, although a relatively new airframe, is still mainly a conventional controlled aircraft. It does have fly-by-wire spoilers, but that is not as significant compared to potentially the A320, which is introduced in 1987 and in fact one of the first fully fly-by-wire aircraft in the world. Instead of using metal cables, it would use electric signals to drive those actuators. And this provides the opportunity to incorporate computer systems into the aircraft. And as a result, with the computers, the A320 have a very innovative feature for its time called flight envelope protection. Essentially, the computer can protect the aircraft by ignoring or amplifying or modifying inputs from the pilot. This can include pitch, yaw and roll, angle of attack, bank angle, speed, and others. For example, the pitch and angle of attack protection can reduce the chance of the aircraft getting into a stall. And also speed. When the aircraft's airspeed is too low, there's a much higher chance of getting a stall. And when the speed is too high, firstly, there can be overload of the airframe itself, and also high-speed buffeting and Mach torque, which is also a very big issue for aircraft control. To understand how the A320 battles the potential of stall, it's important to understand what a stall is in the first place. A stall is when the aircraft reaches or exceeds the critical angle of attack. Shown here, this is an illustration of how an aircraft will potentially stall. A stall is significantly dangerous for aircraft because your wings physically cannot generate enough lift for you to keep flying. There's too much disturbance behind it. On top of it, that differential of pressure is not enough. And another issue that stall can cause is a spin. Because not all aircrafts, in fact, all aircrafts are not exactly symmetrical and each wing can be slightly different. For example, for some aircrafts, one wing may have a pitot tube and the other won't. And maybe there's slightly different icing conditions on both, potentially if the anti-ice is not used appropriately. Then the wings will stall at different angle of attacks and at different speeds and at different pitch, essentially at different angle of attacks. So that means you can get to a very problematic spin. And what's worse for an airline is that stalls usually happen at lower speeds and lower altitudes. That means it's significantly more difficult to actually recover in time from a spin. So this is where alpha protection comes in on the A320 fly-by-wire. Alpha is short for AOA, which is short for angle of attack. And as I've mentioned, angle of attack is the difference between your aircraft's chord line, the wing chord line, and your direction of flight. Essentially, in simple words, the difference between where you're pointing and where you're going. When it goes too high, then you stall. You can look back at the illustration. During the stall, the plane is going like perpendicular to the flight path. Although this is a very exaggerated graph, it is still possible to have potentially 90 degrees or even more AOA for an aircraft. There are two main components to elements that leads to the AOA, and the first is airspeed and the second is altitude. When airspeed is low, to maintain the same altitude, you will require higher AOA. And the altitude will also pretty much directly affect the angle of attack, because when the altitude is high, the angle between your chord line and your flight path is just higher. So the way the alpha protection works is to firstly restrict the attitude. When the aircraft is sensing a stall, then it will ignore any further pitch up input from the pilot, or even maybe provide a little bit of its own pitch down input to avoid reaching or exceeding the critical angle of attack. And another way of protecting the aircraft from stall is called alpha floor, which is when the aircraft goes very close to a stall, it will automatically ignore all the pilot's input in terms of thrust and just provide full toga thrust on the engines. This can significantly reduce the chance and even eliminate the possibility of getting into a stall in an A320. This is an illustration of the difference between aircraft with alpha protection and one without. You can see the first one in green that it will limit its pitch and also provide potentially higher thrust, so it can maintain its attitude and maintain its altitude without getting to a stall and doesn't reach the critical angle of attack. For the second aircraft in red, it does not do that, and not only does it not provide extra thrust, it also pulled a significantly higher AOA. As a result, it stalls. Another feature of the Airbus fly-by-wire is bank angle protection. Essentially, this is a bit more easy to understand. With bank angle, when you're flying straight and level, all the lift is supporting the aircraft upwards. There is the most upwards lift for the aircraft. Once you get into the bank, there's two issues. First of all, the lift gets split into two different directions. If you look at it horizontally and vertically, the lift, some of them will bleed for the turn. So that's the first thing. You need to pull a higher angle of attack to maintain altitude during a turn, during a bank. But the issue is that during a bank, there is your critical angle of attack is also lower. So this will push you to a corner that is a bit less flexible than potentially flying straight and level. And when your bank angle is too high, this corner gets smaller and smaller, and it's very easy to get into a stall or lose significant altitude. As a result, for the bank angle protection in a flight envelope protection on the A320, it does two things. Firstly, it will ignore any further input from the pilots once they reach 67 degrees. It will limit the aircraft to 67 degrees of bank. That's the most it can go without potentially getting too risky. And also, although the A320 is a fly-by-wire and it works very much like a CWS on a 737, the control wheel steering, where it will keep the aircraft's attitude, it doesn't do this when it's exceeding 33 degrees. Once the pilots put their control, stop putting extra control, the aircraft will automatically provide some aileron and spoiler support to allow the aircraft to return to 33 degrees. That's the maximum it can maintain at a longer duration. Of course, in 1987, when the A320 first came out, there is quite a lot of criticism for the redundancy and safety of fly-by-wire, since it's completely relying on the computers. So there is a very comprehensive list of redundancy systems for the A320, and in fact, it is the case up to today, with all the newer aircrafts also maintaining similar or even better forms of redundancy for their systems. On the left of the PowerPoint, there is a screenshot from the A320's flight control status page on the A320's cockpit screen. And on the left rectangle, there is the ELAC computers, ELAC 1 and 2. Those are the ones that will control the ailerons and elevators normally. And on the right, there are SEC 1, 2, and 3. Those are used to control speed brakes and spoilers. But there's a reason there are 3 SECs, and I will explain later. On the right, there are 2 pictures, and those 2 are just the overhead panel of where the pilots can potentially turn off or turn on the ELAC, SEC, and also FAC computers. Although I will not dive too much into FAC, because FAC is mainly for the rudder, and also used to calculate the critical angle of attack. Although it's important and also a factor within the fly-by-wire system, it's not significantly crucial for the basic flight. So here is a graph of how the ELACs will control the aircraft. So normally ELAC 1 and ELAC 2 will just control aileron and elevator, as they should. And SEC 1, 2, and 3 will just control the speed brakes and spoilers. But if, for example, ELAC 1 fails or lose electric power, then ELAC 2 will be used to control both aileron and elevator. Those computers are all able to multitask for different roles. And at this point, the aircraft control will be slightly degraded with potentially a bit less actuation or less speed brakes and spoiler usage. And that is because it's asking one computer to do 2 computers' job. And if both ELACs fail, then the SEC computers are capable of multitasking and switch over to control aileron and elevators. At this point, the aircraft's control will be significantly restricted, because although aileron and elevator are still functional, the speed brakes, all of them are only controlled by SEC computers, and SEC3 and SEC3 it's only one computer and it's doing 3 computers' job. So as a result, usually at this point, there will be essentially half or even less speed brakes or spoilers as operational. But at the very least, the aircraft still be able to be controlled. It's not an uncontrolled flight. If SEC1, or in fact, if everything fails, if all computers fail on the aircraft, say there's a electric failure, then Airbus have incorporated the older systems, the cables, back into the equation. There is a mode in the Airbus A320 called mechanical backup, where the rudder and trim in the cockpit are connected to the cables. And this can provide a very simple but also very sluggish way of controlling of the aircraft. Firstly, trim. Trim is just the trimmable horizontal stabilizers at the back of the aircraft. It can move the entire tail of the aircraft essentially, and that will provide a little bit of nose authority. It's a lot more sluggish and a lot slower to actuate, but it can maintain normal flight. And then secondly, there's rudder. Rudder on the A320 is, like most aircraft, offset from the center of mass. That, as a result, when you actuate the rudders, not only can you create a side slip, you can also allow the aircraft to actually roll a little bit. More importantly, why the rudder can control the roll is because during the side slip, one wing will have a higher airspeed than the other, and the wing with higher airspeed will have more lift, and that means the wing will be raised. So it is still possible to control yaw and roll with rudder during mechanical backup. That means it's technically possible to land an aircraft with mechanical backup, although it's never intended to, because the computers are so redundant that it's never designed to have all of them fail, and mechanical backup is just used for potentially temporary usage, temporary control of the aircraft when, for example, when the flight crew would deploy the RAT, which during that time may not provide as much electrical power. There is one instance though that the mechanical backup was actually used to land the aircraft, and that is during a SmartLynx line training flight for its pilots, and it's fortunate that they have managed to land the aircraft with both engines fail and mechanical backup. And after that, there's no other cases that I know of that have utilized mechanical backup as a last resort. Mostly the ELAC and SEC computers will just come back because of either redundancies or also just electrical power resuming, and there's no need for mechanical backup usage.